everyone to our second seminar on topological optomechanics. After the two exciting experimental talks we had last time, we have two talks by brilliant theorists today. Before we get started, let me briefly remind you of the house rules. Please keep your camera off and yourself muted during the talks. You have the opportunity to ask questions after the talks. You can either raise your hand and unmute yourself, or you can type the question in the chat and we will read it out. And if you are joining us from YouTube, just type your question in the chat and we will forward it to Zoom. The first speaker of today is Tirth Shah from the Max Planck Institute for the Science of Light in Erlangen, Germany, and he's done some exciting research on topological phonon transport that he wants to talk about today. So we're very excited for your talk, and Tirth, the stage is yours.
Can you see my screen?
Perfect.
Okay. Yeah. So thank you for the invitation and the introduction. So I'm very excited to share my work. Okay, so this work is about topological phonon transport in an optomechanical system. And it's a joint collaboration between Florian Marquardt's group in Erlangen, Germany, and Oscar Painter's group at Caltech, USA. So before going towards what we are doing, I want to have a brief introduction to what is topology. So basically, topology is it's actually a mathematical field which deals with properties that are invariant under continuous deformation of objects. So for example, you can deform a cup to a cloth hanger, but you cannot deform a cup to a cheese. So continuous deformation, because they have different number of holes. So cup and cloth hanger both have one hole, so you can continuously deform them, but cheese has many holes, so you cannot continuously deform it. Now, the whole idea is, can we have a phenomenon in physics which also is robust using some same type of reasoning? So one simple phenomenon is the charged particle in a magnetic field. So for example, if you have a charged particle which is initially located somewhere in the center of your region, so it will just have cyclotron orbits, something which is shown over here. But if the initial position is close to the edge, then it will move along the boundaries of your sample, let's say in counterclockwise direction, like this. Now, even if you deform your boundary from square to any arbitrary shape, even then the transport along the boundary is always counterclockwise and it's robust. So this is an example which is a phenomena which is topologically protected, and it's called topological transport. Now for our case, we want to have topological transport of vibrations. So vibrations are actually uncharged particles, so they cannot be deflected with magnetic fields. So how should one proceed with this problem? So the idea is the following. One needs to make a metamaterial. So for example, if you see on the left, if I excite vibration at this point in some structure, then if it is an isotropic material, then the vibrations would just travel along circular wavefronts as shown here. But now if you pattern some holes in your structure, so basically you make a metamaterial and you pattern it in some specific way that if you excite vibration at some point over here, then the vibration would travel along some path that you want. And at the same time, it should not have any backscattering at the corners. So whenever I say topological, I actually mean that there is basically practically no backscattering at the corners. And at the same time, in our work, we also want to measure these vibrations using cavity-optomechanical readout. So basically, our work is a combination of two fields, which is topological transport and cavity-optomechanics. But over here, when I say that topology is actually same as no backscattering. Why is this the case? So I just want to briefly explain why is it so, but one slide is actually not sufficient to explain it in detail, but it still gives some idea. So for example, if you consider a two-dimensional periodic crystal, so which is this, so for example, it could be electronic wave functions in a crystal, or it could be uh, engineered periodic crystal, which is like over here. So for such a periodic crystal, one can have plot band structure. So the solutions of Schrödinger equation, or for mechanics, maybe equations of linear elasticity, will have block waves, and these block waves can be represented in a band structure. So if you have a 2D crystal, then you have kx and ky, which are the two conserved quasi-momenta, and you can have some bands in your system. Now, each band is characterized with something called a topological invariant, which is an integer. And this can only change if two bands intersect. Otherwise, it always remains conserved. So one famous example of a topological invariant is a Chern number, and there are even others, so like spin Chern numbers, valley Chern number, and so on. But the important point is that it's an integer. Now, there is a very nice theory in topological physics, which is the bulk boundary correspondence, which says that if you now connect two different bulks, so for example, bulk 2 has a Chern number 0 for the lower band, and bulk 1 has a Chern number +1 for the lower band, then you can show that at the interface there will be an edge state. So there will be a state which is moving along the right direction because the slope is positive in the band structure, and this is robust. So even now, if you make an interface which is not straight but some arbitrary like this, even then this state will move along the interface without any backscattering. And that's where topology comes, and that's how topology is related to the no backscattering, in short. But now let's look at the literature of topological phonon transport. So if you plot all the experimental implementations until now, so x-axis is unit cell size and y-axis is the frequency of the vibrations, then you can characterize all the experimental implementations as transport in discrete systems, so pendula or gyroscopes, or transport in acoustic waves, or transport in elastic plates. So for example, the pendula or gyroscope discrete systems are of the order 10 centimeters and 1 hertz. The acoustic systems are of the order 1 centimeter, 10 kilohertz. Now, in elastic systems, there is macroscopic systems, so which are of the order 100 kilohertz. But our work lies in this range, which is on chip and in the micro or in the nanoscale. So, for example, in this range, the first experimental implementation was from the Rio group in 2018, where they used a piezoelectric material to excite some vibrations in the system. For our case, we have a cavity-optomechanical system, so we want to use light to measure or excite the vibrations. And our work is actually the highest observed mechanical frequency of topological vibrations in the literature until now. Okay. Okay, before also there's why usually people care about designing these topological waveguides. So what's the motivation behind it? So the motivation comes from two reasons. One is inspiration from solid state physics. So these topological phenomena are very well understood for the case of charge particles in a magnetic field, for example, in quantum Hall effect. For spins, like there is also quantum spin Hall effect, which was very well understood in 2005. Now the whole aim is like, can we have similar phenomena for bosonic particles, so which are uncharged particles like photons or phonons? So the whole idea is, can we take the ideas from well-studied physics for charged particles to bosonic particles? Another motivation is potential applications. So for example, these systems are robust against disorder, so you can have transport without any backscattering at the sharp corners. And this property can be utilized to make topological delay lines or topological lasers. Another property of topological transport is non-reciprocal transport. So for example, you can have transport in one direction but not in the other. So this could be used to make topological switch or topological amplifier. Um, and now, why cavity optomechanics? So, so our work is a combination of topological transport and cavity optomechanics. So I would give some motivations. Why do we want to use cavity optomechanics for our case? So this cavity optomechanics, well, the basic system is the single mode optomechanical system where there is an optical cavity field which interacts with a mechanical oscillator, and which I can represent in this schematic way as shown here. So yellow is a mechanical mode and blue is the optical mode. Now people went from the single mode optomechanical system to multi-mode systems over the past decade. So for example, in multi-mode system, one can have two mechanical modes, one optical mode, or one mechanical mode, two optical modes. And people have shown many applications with such systems like wavelength conversion, non-reciprocal state transfer, entanglement, squeezing, nonlinear dynamics, and so on. So now one could also make an array out of such systems, which is shown over here. So it's an array of single mode systems, and one could have optical coupling between different arrays and also mechanical coupling. So basically all the works, or I would say most of the works in this series of topological optomechanics falls in this category of optomechanical array. And we want to use cavity optomechanics because this opens up the whole range of applications which are very well known in the field of cavity optomechanics, and we can use it for topological transport. And by the way, for our work, the optical coupling is 0 and mechanical coupling is non-zero. Okay, so much for the introduction, and let's go for what we are actually doing. So in our case, as I said, that we want to come up with some pattern of holes. So we want to build a metamaterial. And for our case, so we have a silicon slab, and in that we pattern holes in the shape of snowflake, and these holes are arranged in a triangular lattice. Now in between the holes, we have this embedded photonic crystal cavities, which are shown in yellow. And the idea is that we want to shine laser light at this photonic crystal cavities, and we measure mechanical motion. And the whole reason we want cavities, it's because the measurement sensitivity could be enhanced by the order of finesse of the cavity, which is for our case is order of 10 power 5. Now, there is also, so this system, this is an optomechanical crystal because we have a mechanical mode, which is like a crystal, which a mechanical mode, which is a block wave. So it's which can travel in the whole crystal, but we have localized optical mode, which is photonic crystal cavity. And I say multiscale because our mechanical properties are mostly governed by large snowflake shaped holes, while our optical properties are governed by small photonic crystal cavity holes, hence the term multiscale, because they are of different order of magnitude in length scales. And it was actually not easy to come up with this design. So like we had to satisfy many criteria. For example, we wanted spectrally isolated Dirac cones. So I would come to it in the next slide. We want to have a structure which is feasible to fabricate with electron beam facilities. We also want to have a structure which has a good optomechanical coupling. So for our case, it's 40 kilohertz, the unit cell optomechanical coupling. And we also want high optical Qs, which is 10 power 5. So let's see how we build a topological waveguide with our structure. So when you see this bulk unit cell, so the unit cell of the bulk is in the shape of a kite, which is shown over here. And I want to introduce two parameters for our system. So let's say the radius of holes in this triangle is RA and the radius of holes in other triangle is RB. Now when RA is equal to RB, this system has basically almost a mirror symmetry about this line, and it's also C3 symmetric. So one can show that there will be Dirac points at the K point, which is over here. Now, if you break mirror symmetry about this line, then you can show that there'll be a gap in the Dirac cone, which is shown like over here. And here I also want to introduce that why. So we have a particular type of mode, which is a breathing mode, which has a good optomechanical coupling. So for example, if I play the animation, so the optical cavity is over here. And as you can see that wherever there is an optical cavity, the mode is breathing. So if it is completely red, means it's expansion, blue is compression. So it expands, compress, expands, compress. So it's a breathing mode. And it's good to have so such modes have good optomechanical couplings. Now let's see how we create topological waveguide. So we create two domains, domain 1 and domain 2. So in domain 2, let's say in domain 1, so the optical cavities are in the top triangle, and in domain 2, the optical cavity is in the bottom triangle. So basically, you are interchanging RA and RB in the two domains. And now you can show that for such case, there'll be an edge state at the interface of the two domains. So if you plot the band structure for the waveguide, there is an edge state in the bulk band gap, which is shown over here. So note that for our case, we never break any time reversal symmetry. So we always have have a right moving mode and also a left moving mode for each frequency. At the same time, notice that the two modes, the left and right moving modes, are localized at the values K and K prime. So that's why this is also known as valley Hall effect, because these valleys act as pseudo spins in the analogous quantum spin Hall effect. So let's see how we test our structure in the experiment. So now we create two domains, domain 1 and domain 2. And these edge modes should travel either clockwise or counterclockwise along the domain wall interface. And now if we want to measure the motion so if we want to measure the vibration, so we have a tapered fiber, which we bring, let's say at this point, and we shine laser light at cavity frequency plus mechanical frequency. Now there will be two side bands, and the side band which goes towards the cavity is enhanced, and this is what we actually measure. So we would see a standing wave spectrum in our optical measurement. So this standing wave spectrum is basically the whispering gallery modes of the vibrations which travel along the interface. Now the whole idea is these are thermal vibrations, and we want to check whether these vibrations do not have any backscattering at the corners. But how do we look at this phenomena in our spectrum? So the idea is, which I showed over here schematically. So for example, if there is no backscattering at the corners, then the standing wave modes would be degenerate modes, which are basically right and left moving modes in the triangle. But if there is some backscattering, then this degeneracy would split up. So there will be some splittings that one would see. And in our experiment, if one observes such splittings, it would mean that there is some backscattering. But for our case, we do not see. So for example, what we measure is the following. So let's look at this plot. So the x-axis is the frequency of vibration and y-axis is the side number. So we measure the vibrations at different sites along this triangle, and the color represents the vibration energy. And as you can see that if there would not be any backscattering, then the intensity should be constant, at least in the middle of the side, and which is what we actually observe. So for example, in below, I show that what would have been the spectrum if there would be 0.9 backscattering, so if the transmission would be 0.9 at the corners of the triangle, so one would see some splittings of the waves, one would also see some fringes, but in our experiment we do not measure. So it's an indirect evidence that there is very little or practically no backscattering at the corners. Another way one could test this like how robust is our system is the following. So one creates two trees, so they have different shape. So for okay, before that, so the interface between domain 1 and domain 2 is in the shape of a tree, and now I create two different types of trees. So they have the same circumference and also the same number of corners, but the shape is different. So for example, this side is shorter than this side. Now the idea is, if there would have been no backscattering at the corners, then the standing wave spectrum or the whispering array mode spectrum should be identical for both the trees. But if there is any backscattering, then they should not be have the same spectrum. So this is what we want to test in the experiment. So in C, I show our experimental observations where we see that both the trees have the same standing wave spectrum. And below, I show what would have been the spectrum if there would be some backscattering at the corners. So for example, if there is 0.95 transmission at the corners, then this you can see, if you look at it carefully, that both the trees have a different spectrum. And if it is 0.6, then it's really very different. So this was a better evidence than the previous one to show that these vibrations are actually travel without any backscattering. So the conclusion of our work is basically we measure this topological thermal vibrations with cavity-optomechanical readout. It's actually the first evidence I know in the literature of such a measurement. So measurement of thermal topological vibrations. Also, we have in this process, we have introduced a new design concept of multiscale optomechanical crystal. So the optical mode is governed by small holes, while the mechanical mode is governed by big holes, which is unlike the usual optomechanical crystals observed in the literature. We showed like robust or topological transport of vibrations without any backscattering. We have highest observed mechanical frequency of 300 megahertz in the literature. And in the future, we would also want to go to the higher cooperativity regime, where one could also manipulate vibrations with light. So right now we are just basically measuring the vibrations, but if we could go in the higher cooperativity regime, then one would be able to use the real power of cavity optomechanics, that one could manipulate vibrations. And we would also like to go to even higher frequencies. So for example, few gigahertz. Then if we put our system in dilution refrigerator, let's say of order 1 Kelvin, then it would have phonons of like very few number of phonons of the order of 1 phonon. So that would be really good, that we would like to do it in the future. So this work, I would like to thank all my collaborators for this work, and also the funding source OMT. And thank you.
Thank you very much, Tirth, for the excellent talk. Really interesting and impressive. Do we have any questions? Maybe I can start with one. First, on your Outlook slide about you mentioned the quantum regime. Do you have any concrete ideas what you would like to explore if you get there?
So actually, we do not have any concrete ideas as of now, because experimentally it's not easy to make the system even more smaller. But let's say one would like to couple two different superconducting qubits with such a topological waveguide. That would be the one of the thing that one would want to do.
Interesting.
Mm-hmm.
Maybe I can ask another question, something that I I thought about. You mentioned topological robustness and protection. Is there a difference between, or is there a difference between the two, or is there something on top of the? So what I suppose what I'm asking is there some symmetry that protects your protects your system here in this case?
Okay, for the Valley Hall effect, there is no symmetry which preserves, uh, which uh, which protects the, like, because of which there is no backscattering. Over here, the only reason why there is no backscattering is because one needs to have a large momentum transfer between the two valleys in order to have
Okay.
backscattering. So one mode is localized in valley K prime and another one is in localized in valley K, and these are very far from the point of view of quasi-momentum or in reciprocal space.
Okay, thanks. Yeah, that makes sense. Do we have any other quick question? Otherwise, I think it makes sense to move on. I don't see anything for the moment. So then let's move on. You can get ready. So the second speaker of today is Aash Clerk, and I believe most of you in the audience will know of his work, as he's contributed considerably to the field of optomechanics and also beyond to quantum optics, theoretical condensed matter physics, and quantum information. He's a professor at the University of Chicago and has received numerous fellowships and prizes in the past. For example, he is the Simons Investigator in Theoretical Physics since 2020, and he also received the Rutherford Medal of the Royal Society of Canada in 2015. His research interests are very dispersed and mainly focused on driven dissipative quantum systems, particularly quantum optics and optomechanics, but also superconducting circuits and qubits in the context of quantum information processing. And in recent years, he also started to look into the role of topology in driven dissipative quantum systems, in particular in the context of what is often referred to as non-Hermitian topology. So this is a different notion of topology compared to what we've seen in the previous talks. And this is essentially what he wants to talk about today, and also applications of this in the realm of sensing and non-equilibrium steady states. So thank you very much for joining us, and we're looking forward to your talk.
Great. So yeah, thank you so much, Clara, both for the very kind introduction and the invitation to speak. It's a real pleasure to be here. Hopefully I am awake enough to give a talk. I'm not normally the best morning person, but we'll see how it goes. I had a lot of coffee. Okay, so the title of the talk may be tweaked a little bit from what was advertised. Non-Hermitian quantum lattices, surprises and opportunities. So I think, as many of you know, there's a lot of excitement about some of the unique features of what people call non-Hermitian dynamics in lattice systems. A lot of this work has been done in the context of classical optical systems, classical metamaterials. There's been a lot of work even in sort of traditional condensed matter areas. What I want to tell you about, hopefully in a gentle way, is that a lot of these ideas are still interesting in fully quantum regimes, right? Where we really don't just think about a non-Hermitian Hamiltonian, we really think about an open quantum system. And that some of these interesting surprises and opportunities are maybe even accessible in optomechanical platforms where you really have control over some multi-mode system. So I'll try to give you a gentle introduction to these ideas, introduce some of the main concepts, and then maybe tell you about two pieces of work coming out of my group. I think things that Clara already hinted at, the idea that you can use these sorts of non-Hermitian quantum lattice effects for a very surprising kind of powerful quantum sensing application. And also that there's some sort of interesting non-equilibrium physics that comes in when you start to ask about what are the steady states that emerge under this dynamics. And there's a really surprising thing that breaks down. We normally think about timescales and length scales being connected. That can fail in a spectacular way in these systems. So I'll try to give you a sense of these ideas and also be mindful of time so we have time for questions. I want to start just by highlighting the people who actually did the work. So a lot of what I will tell you about is really the work of a PhD student in my group, Alexander MacDonald. Also bits and pieces of what I'll tell you about really important contributions from Ryo Hanai, who was a postdoc in my group, and Yuxin Wang, who is still a grad student in my group. Okay, so this is an optomechanics, series of talks. So I should start with, every optomechanical talk has to write the optomechanical Hamiltonian and show you these pretty pictures of different optomechanical devices. So we all, I think in this audience, know about optomechanics. We know about this cartoon. We know about this radiation pressure Hamiltonian. We also know that one of the big resources in optomechanics isn't just this Hamiltonian, it's actually the dissipation, right? The dissipation of the cavity, right? We can control how the mechanic sees that by using this radiation pressure Hamiltonian. And we can use the dissipation to do interesting things. And the thing that most of us have heard something about is this very general idea of reservoir engineering. So we can use dissipation as a quantum resource to basically prepare degrees of freedom in interesting steady states, right? So we have some non-trivial dissipative reservoir. Maybe that's our driven cavity. It's talking to one or more mechanical degrees of freedom. This non-trivial dissipative reservoir relaxes and stabilizes the mechanical degrees of freedom in some interesting state. So you can view sort of cavity cooling as an example of this. There's more fancy versions of this idea where people have demonstrated dissipative squeezing in optomechanics of a mechanical degree of freedom, even dissipative entanglement, right, of two mechanical modes talking to a common reservoir. So in this talk, the focus is going to be a little bit different. We still want to think about using dissipation as a resource, but the goal is not now reservoir engineering. The goal is not state stabilization. So what's something else we can do with dissipation? We can use dissipation to make two systems. Think of two mechanical modes. We can make them talk to one another in a way that's very, very strange, in a way that you can't really describe with a conventional Hermitian Hamiltonian. So the idea is to try to understand and sort of use as a resource these funny, let's call them Bath-mediated interactions. Okay, and so these are things that at some level of approximation, we can describe with a non-Hermitian Hamiltonian. And I'll give you an example in just 30 seconds. And it also enables new kinds of functionalities. Let's consider a concrete example. So imagine my two systems are two mechanical modes, and maybe they're going to talk to some common dissipative environment that's going to be some driven sort of photonic modes. And maybe the kind of funny interaction we want that is going to be mediated by this reservoir is a kind of beam splitter interaction or tunneling interaction where we can think of phonons moving back and forth between those two modes, but in a way that's non-reciprocal. So here I've written down the first of many non-Hermitian Hamiltonians in this talk. We have a simple tunneling or beam splitter Hamiltonian, lowering operators for phonon mode 1, phonon mode 2. And you see now that the amplitudes, right, for tunneling from 1 to 2 versus the backwards process, they differ in magnitude. So this epsilon here is supposed to be a real parameter. The epsilon dependent terms here make this Hamiltonian non-Hermitian. Okay, so very crudely, this describes a situation where somehow it's easier to tunnel from 1 to 2 than the backwards direction, assuming epsilon is bigger than 0. So if I look at the non-Hermitian part of this Hamiltonian, the epsilon dependent terms, I can write that in a little bit more of a suggestive way. I can rewrite the epsilon dependent terms basically in terms of a negative or an imaginary frequency for some new collective mode, right? And what's that new collective mode? It's a linear combination of these two phonon lowering operators with some imaginary coefficient. And this then kind of tells me, what do I actually have to do to build this funny kind of non-Hermitian Hamiltonian? Well, I basically need to selectively damp this funny delocalized collective mode, right? This is just saying that collective mode has an imaginary frequency. That's just another way of saying it's damped. And that's basically what we want to do with this cartoon here. We want to construct a kind of dissipative reservoir that will serve to sort of damp a collective degree of freedom of these two modes. So this is an idea that's actually been implemented in different ways in many, many different optomechanical experiments. Let me just single out one. This is an experiment from Jack Harris's group where we sort of helped out with the theory. So in this experiment, it's a membrane in the middle system. So it's a Fabry-Perot cavity. There's this silicon nitride membrane, a millimeter square. The two mechanical modes are two, normal modes, two, drumhead-like oscillation modes of that membrane. The way they're going to talk to one another in this funny non-reciprocal way, it's the light in the cavity, this lossy Fabry-Perot cavity that's driven with laser beams, that will act as the funny dissipative reservoir that gives rise to this sort of one-way phonon tunnel. Okay, and so, I want to get on to other things, but basically this experiment and others basically show that yes, by controlling the properties of the light in the cavity, by driving it the right way, you can have the light in the cavity act exactly like the kind of dissipative reservoir you need to have this one-way phonon tunneling. So this is just one of many results from that experiment, that with this non-reciprocal interaction turned on by driving the light during this kind of gray region, you can have a situation where if B is initially excited and A is not, there's really no transfer of energy between the two modes. But if you flip around the initial condition, start with A excited, B not excited, well, then you can basically have a transfer of energy. Okay, so this is all kind of background. Again, this idea that getting these funny non-Hermitian, and we can even say non-reciprocal, right? There's a sense of directionality, right, in this Hamiltonian. It involves using structured dissipation. It involves using dissipation to sort of mediate interactions. And the real focus of this talk is now, let's leave experiments and jump to the land of theory. Well, if you can do interesting things with just two modes interacting in this funny way, what if we could dream a little bit and really build a multi-mode system, a lattice system, where, again, imagine each of these is a mechanical mode. Sitting on each bond of this 1D lattice is an optical mode that's driven in just the right way to make the tunneling, right, between these two elements directional. Non-Hermitian, maybe tunneling to the right is stronger than to the left. Okay, so there is a path that I've just sketched to get this sort of functionality in optomechanics. The real question I'm going to focus on here is, let's step back and just think about the theory. What happens when you take this kind of directional physics, take it to the level of the lattice, right? How do we think about the physics? What is the physics like in truly quantum regimes, where we go beyond just this non-Hermitian Hamiltonian? And is this physics actually good for anything? So those are the things I'm going to try to tell you at least a little bit about. So let's try to build up the, in a sense, it's like the hydrogen atom or the simple harmonic oscillator of a non-Hermitian lattice model. So the simplest Hermitian lattice model, right, that we all saw in some solid state physics class is just this 1D type binding chain, some hopping matrix element W, right? The simplest non-trivial non-Hermitian extension is just to make these hopping matrix elements now non-reciprocal, right? So let's have the hopping to the right be larger in magnitude than the hopping to the left, okay? And so kappa here and W here are real parameters. Let's take kappa to be greater than 0. So this is actually an old model. This is known now as the Hatano and Nelson model. It was first studied by these authors, not motivated by some deep love of non-Hermitian physics. It was motivated by studying sort of a flux line physics in superconductors. They thought about it as an imaginary vector potential. That's another way you can think about this. And again, the crucial thing here, it's not just non-Hermitian, right? Just adding gain and loss by itself, that by itself is maybe not the most exciting thing. The exciting thing is the non-hermiticity, right? These kappa-dependent terms, they're non-local. There's a sense of directionality here. Okay, so what's the physics of this system? Well, there's actually a lot of surprising physics of this Hamiltonian. Let me tell you about maybe what is one of the most shocking things and maybe most exciting things about this Hamiltonian. And this connects to sort of very general notions of topology. So to really oversimplify what's one really amazing thing about conventional topological systems, it's the bulk boundary correspondence, right? So there's actually interesting and surprising things that happen when we go from periodic boundary conditions to open boundary conditions, right? We know about these protected localized edge states that can emerge because of topological reasons. So what happens with this simple kind of non-reciprocal type binding model? So if you start with periodic boundary conditions, that is, make your lattice into a ring, you have translational invariance. The eigenstates of this non-Hermitian Hamiltonian are plane waves, right? And you can basically write down the dispersion relation. And look, it's a non-Hermitian matrix. And so the energies, right, are complex. So if I plot them in the complex plane, they form this kind of ellipse structure. And that also tells us another way of thinking about this physics, right? This is my ordinary tight binding dispersion relation. This is saying I have some damping of these momentum modes. Oops, jumping ahead. And that damping is actually momentum dependent, right? So that's another really powerful way to think about what we're doing here. Okay, so no big deal, non-Hermitian matrix. We have some complex energies. Well, look, it's non-Hermitian. There's damping and anti-damping in the system. So now what happens if you just cut one bond, right, and make the system have open boundary conditions? And even though I'm just showing something with 5 sites here, this is physics that works if you have 10,000 sites. And so the shocking thing is, it's not just a question of, oh, I cut the ring, I get some localized edge states. The entire spectrum of this non-Hermitian Hamiltonian changes. So with open boundary conditions, this is now the spectrum. All of the eigenvalues are completely real. And further, if you actually look at the wave functions, so with open boundary conditions, they have to be plane waves. We have translational invariance. With open boundary conditions, we actually find that the wave functions, the right eigenstates of this non-Hermitian Hamiltonian, are localized. They have an exponential envelope that's controlled by the degree of non-reciprocity. So this is sort of a very dramatic effect, right? And really weird coming from the land of solid state physics, right? Changing boundary conditions isn't just about surface or edge physics. It seems to change the physics completely, right? The spectrum and the nature of the eigenstates. Okay, so there is a way to think about this physics or try to connect this physics to some notion of topology. So, you know, if we're going to do something topological, I need some notion of some topological invariant, right? Some integer that characterizes my system and is hard to change. Well, with these non-Hermitian systems, unlike their Hermitian counterparts, we don't even have to look at the wave functions and the phases of the wave functions to get some notion of winding in topology. You can just look at the spectrum and go, oh, wow, that spectrum basically winds, right? So if I pick the origin over here and I vary k, right, the spectrum as a function of k sort of maps out this ellipse. In this case, I get this winding number of 1. So there are interesting ways to try to connect the existence of this winding number, which you can really view as a topological invariant, connect that to the fact that there is this, what people call a non-Hermitian skin effect, this dramatic change when you go from periodic to open boundary conditions. And here are many, many works that go through that. If people have questions about that, I could talk about that more, you know, during the question section. What I want to focus on here is there's actually an easier way to understand why we have this dramatic physics. This more physical way of understanding why this comes about also lets us think about how we might exploit this for applications, okay? And the simple way of understanding the physics here, let me even just go back one slide. If we look at the imaginary part of these eigenvalues, right, when we have periodic boundary conditions, right, depending on the sign of this factor here, I either have damping of a particular block mode or I have anti-damping. What's anti-damping? That's some notion of amplification. So the crucial dynamical picture for how do I think about a particle actually moving on this lattice is basically what's shown in this picture. So as particles, let's say delta be greater than 0, as particles propagate from left to right, they basically propagate with gain. There's amplification going on, and the amplification is directional. Okay, so it's actually a simple exercise. You could calculate the Green's function or the susceptibility for this model. So if you inject a particle on site M, let it propagate for a time t, remove it from some site n, what's the amplitude for that propagation? You find that there's an exponential factor that's either exponentially large or exponentially small, depending on the direction you go in. Okay, so the dynamics here involves amplification. Why does this let me understand the sensitivity to boundary conditions? Well, if I have periodic boundary conditions, if I have a ring, you can imagine injecting a particle going around the ring forever, right, in the correct direction. You get amplified forever and ever and ever. That's an instability, right? So that instability is what's giving rise to these kind of complex eigenvalues. If I now change the boundary conditions, right, so I can't form a complete loop. All I can do is bounce back and forth between the boundaries. Now there's no possibility for instability, because now if I get amplified going from left to right, hit this wall, as I come back from right to left, I get de-amplified. Okay, so this simple cartoon picture can be made more precise. This is another way of understanding a lot of the surprising physics of these systems. There's this notion of chiral amplification. And let me just do a little plug here for our organizers. Really nice work. So Clara, Andreas, and sort of coworkers, they also have a nice series of papers using this idea of chiral amplification and connecting it to notions of topology. Okay, so this is now, in a sense, what is perhaps the most exciting and dramatic non-Hermitian lattice effect. I want to now tell you a little bit about what could we actually do with this effect in a quantum system. What can we do with this effect that maybe is actually useful? Okay, and so the first question we could ask is, well, look, I have a lattice, it has 10,000 sites. I break one bond, things seem to change dramatically in the properties of this system, right? So if you know anything about quantum sensing, right, a lot of quantum sensing boils down to trying to estimate some very, very, very small parameter in the Hamiltonian. When that parameter, I'm going to call epsilon here, changes, you want to get a big effect. You want to be able to see that change induced by changing the parameter, use that to make an estimate of what that parameter is. So it's a really natural question to ask. Can I harness this kind of sensitivity to do some sort of enhanced quantum sensing, right? So I can imagine adding a perturbation to my Hamiltonian, right? So maybe I start with open boundary conditions. My perturbation actually, connects the first and last site. So in a sense, it takes me from the left picture to the right picture. You might think you're going to have an incredible sensitivity to that parameter epsilon. Okay, and why do I say quantum sensing? In a sense, everything I told you up till now, there's no quantum mechanics, right? Despite the hats on this is just some matrix, right? Describing this funny unidirectional propagation. Why things get quantum here is if I really want to understand how well I can estimate this parameter epsilon, I also have to think about fluctuation physics. I have to think about noise physics. I can't ignore quantum noise. I have to worry about the fact that, hey, I'm using dissipation, right? That's what I told you to begin with, to realize the non-Hermitian terms here. Fluctuation dissipation theorem tells me dissipation comes with noise. In the classical world, temperature could be 0. I could turn the noise off. In the quantum world, I always have quantum fluctuations, right? So this now becomes a quantum question because we need to think about fluctuation physics. Okay, and so the obvious way of building a sensor out of this setup is to do what I just said. Start with a chain here, open boundary conditions. Have the parameter just connect the two ends, and then say, how well could I estimate a small change in that parameter epsilon? It turns out this is actually not a good way to build a sensor, okay? And I can discuss this more. If you actually ask, how good is my sensor given how many photons are actually in this change? Let's really think of a a chain of photonic cavities to probe this thing. You're going to send in light. You're going to have photons in the system that are interacting with whatever it is that's giving us this parameter epsilon. If you measure your sensitivity and you constrain the number of photons you're using, it turns out this obvious technique gives you no advantage. The scaling with the number of photons in the system is the same as a much more conventional boring sensor. So it turns out a way of still using some of this physics to do something interesting is to basically double the system. Okay, so what do I have here? Each one of these chains is supposed to be one of these non-reciprocal, Hatano-Nelson chains. But the green chain, I have directionality from left to right. The red chain, I have directionality in the opposite direction. And so now the parameter sensing, we can imagine, is actually a parameter that can couple those two chains. So it turns out this is something that gives you a sensing advantage, even if you say, hey, look, to make a fair comparison against some more conventional system, I'm going to hold the total number of photons in the system fixed. Okay, so it turns out in this system, even if you do that fair comparison, even if you think about quantum noise effects, you can get an exponential enhancement of the sensitivity of the sensor, your ability to estimate this parameter epsilon. And the more precise statement here is you would actually bound, right, the error of estimating the parameter epsilon by looking at the light that's kind of coming out of this waveguide where you sent light into the sensor, it's coming out, right? So this is what people would call a quantum Fisher information calculation. The standard way of doing things, there's really no enhancement if you express everything in terms of the average number of photons in the lattice. That's what this n bar is. This doubled version, even if you express things in terms of the number of photons you're using, there's this exponential enhancement. This A here is basically a measure of the non-reciprocity. Okay, so in principle, this is kind of exciting. In principle, for this kind of sensing, as you make the sensor bigger and bigger and bigger, right, you get a greater and greater and greater sensitivity. The error of your parameter estimation keeps increasing. Again, all of this is for the limit where the parameter you're trying to estimate is kind of going to zero. Okay, so I mentioned noise, and that's kind of a crucial thing. So how do we get this physics without having the quantum noise kill us? And this touches on another big point that I wanted to kind of introduce. It turns out there's a way of getting these non-Hermitian effects in a fully quantum setup without needing dissipation at all. And it also does not require post-selection, doing quantum trajectories, throwing away most measurement outcomes. So there's a really simple way to explain the idea. So these would be our equations of motion coming from our non-Hermitian Hamiltonian, right? If we lived in a classical world, right? So we just treat these photon lowering operators as some sort of amplitudes. Here's this equation of motion. Because things are non-Hermitian, right? There could be a tendency for these amplitudes to exponentially grow or decay. And that's a problem, right? When we now make things quantum mechanical, we know that canonical commutators need to be preserved. I can't just have things start growing or decaying exponentially, right? Because then there's no way this relationship will be, fulfilled. So we know one way out of this problem is to turn this into a kind of Langevin equation, add noise terms here, right? And then those will make sure quantum mechanics is not violated, right? We're obeying the quantum version of the fluctuation dissipation theorem. But what if I don't want dissipation? What if I don't want to add any noise terms here at all? Where there's another route, right? Let's not encode our non-Hermitian dynamics in A's and A daggers. Let's instead encode it in position and momentum, or if you want, the quadratures, right? The real and imaginary parts of these amplitudes. So now I can imagine a kind of doubled version of my system where maybe the X's have a tendency to grow exponentially, but the P's have a tendency to decay exponentially, right? So then this is all okay according to quantum mechanics if I do things right, because I could still have this commutator be fulfilled. So this turns out to be a very, very general route if you really have some interesting non-Hermitian dynamics that you think would be really cool in the quantum regime, and you don't want noise to mess it up, there is a very, very general way to map it onto quantum bosonic degrees of freedom, where you don't need any dissipation at all. You use basically the simple intuition in the last line of this slide here. And for more details, you can look at this paper that I wrote with Yushin a few years ago. So for this sensor problem, where we want these two non-Hermitian, Hatano-Nelson chains, it turns out there's a non-dissipative bosonic quantum model that basically does that for us. So this is, again, a 1D chain of cavities. I have this hopping between them, okay? And the hopping is imaginary, and that's important. And you can ask me about in the questions as to how would you get that. And then we have this term here, which looks like a pairing term. It's creating pairs of photons or phonons on adjacent sites. This is basically a parametric drive in the rotating frame. Okay, and so long story made short, if you write this in terms of x's and p's, right, just our standard quadrature operators, you see that you get something that starts to look like Hatano-Nelson, right? You see that there's a bond that is weaker in strength and a bond that's stronger in strength. And sure enough, if you take the equations of motion for this Hamiltonian, just the Heisenberg equations of motion, right, we basically get two copies of our asymmetric tight binding model. So the x's have a tendency to hop more strongly from left to right than vice versa. And this R parameter is directly related to the asymmetry of these two amplitudes. And the p's kind of have the opposite asymmetry. Okay, so this is really a kind of direct way of getting two copies of Hatano-Nelson without needing any dissipation whatsoever. Okay, very quick thing is, even though I put hats everywhere on this, and there is some interesting quantum things to think about, all of this is stuff you could realize completely classically. So this is trying to indicate a kind of purely mechanical realization of this, where basically to get the kind of two couplings you need here, you could really just modulate the coupling spring constants between each of these masses. Okay, so there is even without even optomechanics, you can imagine doing this all mechanically using a kind of mechanical metamaterial. Okay, so and just so there's time for other stuff. So the way that the sensing now would work, this single chain of cavities with this funny Hamiltonian is actually equivalent to my Hatano-Nelson chain, two copies of it. The way the sensor would work is, what's the parameter of interest now? Well, it's actually just a dispersive coupling. So the parameter of interest is really controlling the frequency of the last site of this chain. The way you do the measurements is you send light in and you basically look at what's reflected out. Okay, and so just to save time, so you send light in, it reaches that last site. It then gets scattered from, so you send the light in a particular quadrature, right? Let's say the X quadrature. It reaches the last site. It gets scattered into a P quadrature. And now it's like it's going to be in the opposite Hatano-Nelson chain. As it propagates back, it also gets amplified. Okay, so that's basically the main mechanism for how we get some sensitivity enhancement. If you now ask about the noise for epsilon equals 0, we can see what happens to the vacuum fluctuations as they go from left to right. They get amplified going from left to right. They don't get amplified going back. They get de-amplified. Okay, so in the limit where this parameter is sufficiently small, we have this nice feature that we basically amplify our signal, right? We amplify the effects of a non-zero epsilon. We don't actually amplify the noise. Okay, so I think, let's just skip that. So here's just some comments on this sensing application. This is sort of the take-home message. There's an exponential enhancement of the sensitivity, right? Even though you keep the number of photons you're using. I stress that all of this is in the limit where epsilon goes to 0. There's never a free lunch. The dynamic range of your sensor, of course, shrinks as the lattice gets bigger and bigger, right? But there is a regime where if the epsilon that you're interested in is small enough, you keep improving your sensitivity by making the sensor longer and longer. Okay, so I think I have order 5 minutes. Let me at least give you a little bit of a flavor of the second story I wanted to tell you about, which now turns to a different question. So, okay, look, we have these interesting non-Hermitian lattice Hamiltonians. We can look at their spectrum. We can get topological notions from that. But we could also ask a question of, well, are there interesting steady states, right, of these models? So often when we think about topology in a condensed matter, think of fermions. We have some topological band structure. We have a Fermi energy, right? We fill some bands are empty. We're sort of interested in that state, that many electron state that has filled some number of these topological bands. So what are the corresponding questions we can ask about these non-Hermitian lattice models, right? And right away we have a tricky thing. I can't just say, oh, here's a non-Hermitian Hamiltonian. I'm in thermal equilibrium. Let me make a density matrix that's the exponential of this H. Well, if this is non-Hermitian, that gives you a non-Hermitian density matrix. Unless we want to think about extensions of conventional quantum mechanics, that's going to be problematic, right? So what we want to do is actually construct a legitimate open quantum system that has the physics, right, of this, for example, Hitano-Nelson chain, but lets us really ask in a sensible way, right? What is a legitimate allowed quantum evolution? What is the steady states of this? So this is just reviewing what I've already told you about for this Hitano-Nelson chain. Big sensitivity to boundary conditions. For an open periodic boundary conditions, we have plane wave eigenstates. For this open chain, all of the eigenstates are localized. There's a kind of localization length here that depends on the non-reciprocity. So kappa is the parameter here that controls how non-reciprocal the system is. And what we'll see is when we want to sort of make this into a legitimate quantum theory, we want the non-reciprocal hopping here. There's no way to avoid also having, let's call it these on-site loss terms. Okay, if I just have the kappas here and I don't add terms like this, we're never going to get a sensible quantum theory. Okay, so the kind of one way of making this Hitano-Nelson model a legitimate quantum theory is to actually model the dissipation that's sitting on each bond that's giving us the non-reciprocal tunneling. So that's this Lindblad master equation. This is the standard Lindblad dissipator. It's describing the correlated damping on each bond, right, that involves site J and site J plus 1, right? So this is like a correlated loss term for each bond. And then we're not going to have an interesting steady state if we have no particles in the system, right? So let's put some particles in our system. You can think of this as just incoherent pumping on each side of the lattice at some uniform rate. Okay, and we're going to be interested in the limit where the main physics is from this W and kappa term. This gamma is just going to be this tiny parameter we introduce. Think of it as like a chemical potential to actually give us some particles in the steady state. Okay, and so that's what I'm just basically writing here. This is just reminding you that, again, when we go from periodic open boundary conditions, or periodic boundary conditions to open boundary conditions, there's this dramatic change in the spectrum. The one difference in this picture, though, is now because if I treat this dissipation properly, I'm never going to actually get any eigenvalues that have positive imaginary part. So in the periodic boundary condition case, and this is now for fermions, we see that this entire ellipse is shifted to be below 0. When I go to open boundary conditions, all of the eigenvalues, right, have the same damping rate, right? They're all sitting here at, at -1. Okay, so what do we actually find in terms of the steady state? So we're looking at a situation where we're introducing just a little bit of extra pumping. That's what this gamma rate is. If we look at things with periodic boundary conditions, there's nothing really that surprising that goes on, right? And here I'm focusing on the case of fermions for a moment. So there's a very, very small dissipative gap in this system, right? There's one mode that's almost undamped, right? So its damping rate is going to 0. Its very, very slow damping rate is just controlled by this gamma. And not surprisingly, that very, very low damping rate, long time scale, gives rise to a very, very long length scale. So this length scale here goes like 1 over the square root of gamma. If you actually look at the steady state of that master equation and look at correlations in terms of where the particles are, you see that long correlation length show up. So none of this is surprising, right? This is all long time scale gives you a long length scale. So the surprising thing is, what if we go to open boundary conditions, right? So now with open boundary conditions, the entire spectrum collapses to this line. We now have what we call a large dissipative gap, right? All of the damping rates in the problem are large. They're order kappa, which is the same as order W. And so what would we expect? Well, there's a large decay rate. There's a very short time scale. We would think that any length scale in the steady state of my system would also be short, right? Short time scale, short length scale. We'd also expect, well, look, for this non-Hermitian skin effect, all of the eigenmodes are localized. And I told you about, oops, this localization length. We'd also expect that that same localization length shows up in the steady state. And so in the 1 minute I have left, I will just tell you both of those expectations are wrong, okay? Both of those expectations do not show up in the actual quantum mechanical steady state. So this is actually just looking at the average density in the steady state of that master equation that describes this kind of non-Hermitian Hamiltonian here. The solid blue curve is for fermions. The dashed blue curve is for bosons. The crucial thing is there's a new emergent long length scale in this system, even though there is no long time scale, right? This is a large damping length. This new large length scale is really controlled by this weak pumping rate. And so for fermions, it gives you this kind of healing length. There's a suppression of the density towards the left. And again, the directionality is from left to right. For fermions, there's kind of for bosons, there's a pileup of particles towards the right. Notice that this is a logarithmic scale. So we can associate a pileup with an exponential localization length. That's this length scale here. Okay, so 2 surprises. There's a long length scale here that despite the fact that there is no long time scale. The other thing is this long length scale has nothing to do with the length scale from the non-Hermitian skin effect. If you just look at the right eigenvectors, you find they're localized. There's this length scale. That is less than a lattice constant on this plot, right? This length scale here, order 50, completely different. Okay, so my timer is telling me I am out of time. I'm going to flash up the conclusions and hopefully leave some time for questions. Hopefully I've given you a flavor of some of the interesting things you can do with these non-Hermitian effects and lattice systems, and the fact that they are interesting in quantum regimes. So with that, I will stop and thank you. Yeah.
Thank you very much, Ash, for the really excellent talk. Do we have any questions? I saw one in the chat, but I would quickly like to go first with my own question, if that's all right. When you talked about the 2 different sensor designs that you can come up with, you showed that you could either have the chain and connect that via epsilon, or you could use 2 chains. When you only have 1 chain and connect them via epsilon, is the problem that eventually the system becomes unstable, or?
Yeah, so let me find the nice little cartoon here. So the question always is, when you want to claim you're doing better, right, with some sensor, and you're going to compare against, just imagine like a simple sensor where it's like 1 cavity, its frequency depends on the parameter, you send in some light, you make a homodyne measurement of what comes out. You need to make a fair comparison, right? So even with a conventional sensor, if I use more photons, right, I can make a better measurement. So you can trick yourself into thinking this kind of setup here gives you an advantage if you don't actually ask, well, how many photons on average are sitting inside the sensor during the measurement? So if you work out the sensitivity here, right, what's the error in your estimate? And then you write things in terms of how many photons are actually in the lattice on average. There's no longer any dependence on the length of the lattice or on the degree of non-reciprocity. So up to a prefactor, you get exactly the same expression you could get with just a single cavity, a conventional measurement, right? And so whether or not you still think that's exciting or not, some people will, argue with me on this. I would say it's not, right? And if this is something you care about, I want to make a good measurement and not use an infinite number of photons. This design, even if I constrain how many photons I'm putting in the lattice, I still get an enhancement with lattice size. Yeah, so the difference is it's really about constraining this photon number.
Okay, yeah, that makes sense. I was just also wondering, if you go to periodic boundary conditions, then eventually you will have some instability, if epsilon becomes very large. I suppose you only care about small epsilon, so then it doesn't.
Yeah, so that's another really good point that was sort of, it's all hidden in this cartoon. So to make the measurement, you're definitely coupling this ideal chain to an extra source of dissipation, which is just your input-output waveguide or transmission line. So that gives you some damping rate kappa. We're always working in the regime where this epsilon is actually weaker, right, than what that coupling rate kappa is. We're really thinking about what you normally do in quantum sensing, that epsilon is going to zero, right? We imagine it as theorists being smaller than everything else. So the instability physics is mitigated by the fact that you have that, that kappa there. Yeah. So we're not ever going into some kind of unstable regime.
Yeah, exactly, because otherwise, I suppose the instability would set in when you have the maximum sensitivity or something like that. So then.
Yeah, so you could think about, so, on some level, if you go into a regime where the epsilon really makes you unstable, then it's never really going to be some linear response type analysis. It's also going to be, it's a different sensing modality, right? Because that means now it's never time independent, right? As I have this epsilon be non-zero, there's going to be some exponential growth process, right? Whose rate or properties depend on the sensor, right? And there are ways to think about things like that, but having a well-defined stationary state, in a lot of cases, is just easier both to think about and to use practically.
Yeah. No, this makes sense. Thank you. So let's move on to the next question. So there's one by Javier del Pino Gutierrez, and he's asking about. Okay, let me have a look. I'll just read it out. Regarding the discussion on the linear coupling and squeezing dynamics in the dynamics of the lattice, so in the bosonic Kitaev chain, I suppose. So how robust is the directionality, and can it be expected when you incorporate nonlinear effects, for example, Kerr nonlinearity in the model?
Yeah, so that's an excellent, question, and clearly, I'm sure we're not the only ones kind of thinking about these things. So that's actually, I didn't really discuss it a lot, but so when we talked about, let me even write down the master equation, right? So this is kind of trying to describe this non-reciprocal chain model using a legitimate master equation. We talked about the physics involving amplification, and for bosons, amplification is okay, right? Amplitudes can get bigger and bigger and bigger. For fermions, it's not okay, right? There's no sense in which a fermionic operator can get bigger and bigger, right? So one of the interesting things already in looking at the fermionic model is the idea of having a kind of hardcore constraint that I can never have more than one excitation on the system. How does that actually disrupt the physics that we think of just classically, that these amplitudes tend to grow exponentially as they propagate? But the full answer of your question, right, if you really think about this physics and you add nonlinearity, the full class of, non-Hermitian lattice models that people have been looking at, I think there's still a lot of interesting things to be done, right? And it's sort of like the same question with like topological band structure, right? So there's a really nice, precise understanding of non-interacting particles moving in some periodic potential, band structures, how are they topological? When you now add interactions, and the interactions are not perturbative, how do you now think about the topology that arises? That's a much, much richer question. And I think people are just starting to sort of think about the analogous questions in these sorts of systems, right? So we are certainly looking at exactly the kind of questions you're asking here, right? So we know we have fermions, we know what happens, right? But hardcore bosons are not exactly the same thing as fermions. And what if the interactions, you talked about Kerr interactions, what if they're not super strong, not super weak, right? What is the crossover? So that's an interesting question. It's theoretically hard question, but it's stuff that I think we and others are looking at. But that's exciting, right? There are things here we don't even know about these systems.
Yeah, that's certainly an interesting question. Thank you for elaborating. And Javier also says, thank you in the chat. We have another question by Ewald Verhagen.
Yeah, thanks, Aash, for a really inspiring talk. Following up a little bit on Clara's earlier question about the sensing enhancement. Yeah. So you motivated going to looking at quantum sensing because, okay, you need to consider fluctuations. But I could argue that any sensor, also a classical sensor, needs to worry about fluctuations. And the noise always limits your sensitivity. So to what extent does this idea also apply to classical noise? And then maybe very specifically, what if the resonators from which you build the chain, what if they themselves introduce a little bit of loss because and noise, because in reality that's always going to be the case?
Yeah. So all excellent questions. So one interesting thing is, yeah, okay, let's first think about the fact that, okay, all of these resonators themselves are actually lossy. So it's not just, I had this very simple picture that I was trying to allude to, that this is the only port where noise enters the system, right? So I can't avoid that because I need to take light or phonons out of the system. But in reality, each of these modes will have some internal loss. There's vacuum or thermal noise entering there. So the way that the amplification physics work, because it's chiral, you're only really sensitive to noise that is injected due to loss at the left edge of the system. Because that noise that's injected, right, can actually like kind of propagate, get amplified through the system, come back. So this is something that is a concern, but it's really the internal loss towards the left edge of the system that kind of dominates the performance. You become kind of exponentially insensitive to what happens to the right edge because that noise is just not going to be amplified the same way. So, okay, so that's one concern. Any thermal noise coming in through the input channel, it's exactly the same kind of analysis. So whether it's quantum noise or thermal noise, the same physics that I discussed applies here. You're amplifying the signal without amplifying that thermal noise, right? And again, this is all for infinitesimal parameter sensing. But yeah, a lot of these ideas, look, at the end of the day, if it's linear dynamics, right, classical and quantum are pretty much going to be similar. It's just, in the quantum regime, you can't ever shut off the noise, right? And I'm sure, Ewald, there's a long, interesting discussion of these non-Hermitian sensors, even without the lattices, of people making arguments that you don't need to think about the noise to characterize sensitivity, and then other people getting upset about that, right? So there's different viewpoints on that, but I would agree, even classically, ultimate limits to sensitivity, noise is almost always going to play a role. Yeah.
Thank you. Yeah.
Thank you very much. I think we could probably discuss for quite some time, but let's wrap it up now. Thank you very much for this really inspiring talk, Aash, and also thank you again to Tirth. I think this was a really nice seminar. And thank you everyone who joined in. Let me briefly advertise what we're doing next. Starting on the 9th of March, we have a block again of 2 seminars on state transfer and measurement, and we'll send out further details via the mailing list. So watch out for these details. Thank you again, everyone, for joining today, and see you next time.
Thank you. Bye.